What's up? Welcome back. In this episode, you'll see how to solve day 8 of the Advent of Code for 2023. This one's called the Haunted Wasteland, and we're going to talk about modulo operator, least common multiple, and a couple other things in this solution that are pretty fun. So in today's exercise, we are given a map that looks like this, and it's helping us navigate through the desert on a camel because the elf we were working with just disappeared. And so this is our input. At the top, we have some list of directions, in this case, right and then left. And then below that, we have a bunch of nodes that map from some node name, and that tells us where we can go from there. So in this case, we can go from AAA to either BBB or CCC. And once we go to BBB, we can go from BBB to either DDD or EEE. And the way that we navigate through this is based on the directions that we're given. We're going to start with the first instruction that says right. And if we start at A and our first instruction is right, then we're going to pick the right node from this possible list. If it says left, we're going to go to the left. And if this sort of directions right and left at the top are repeating forever. In this case, it's just going to say go to the right, then go to the left, go to the right, go to the left. Down below, we have another example. In this case, it's left, left, right with a small list of nodes. So if we start at A and we go left first, and then we go to the left again, and then we go to the right, and then we go to the left again, and then we go to the left again, and then we go to the right, we end up at Z. And our goal is to traverse on part 1 from AAA to ZZZ. And we have some puzzle input, but for now, I think this example actually is more useful than the first one. So let's grab that, crack open our main.rb, and get started here. So we'll start off with our input being some input. And what we need to do first is parse this out. So we've got these directions at the top, or some sort of like turns, and then we have the list of lines below that. So I think what we can do is just, maybe we'll say like data is input dot each line dot map chomp. And then for each of those lines, we want to split this up, and so that we're going to get our like turns first, and then a new line, and then some list of nodes. We'll call it n for now, and then we'll replace that later with an actual nodes variable. Each line is going to give us the split already. Okay, so turns is left, left, right, and then each of our nodes, or like this n, is going to be the string of AAA equals BBB, BBB. So for turns, we want to turn this into characters, so turns dot chars. And then for our nodes, we want is a dictionary of the source node. So we're going to have source node points at an array of target node. And this is going to be like the left node and the right node. So we're building a binary tree of sorts, or maybe like a graph. Yeah, it's a graph, not a tree. So what we want to do now is we'll just say like nodes is equal to n dot map node. And for each one, we want, we'll have the name, and then we'll have the children. But I think we can say, the name and the left and the right is node.scan for word. And this should give us back what we expect. And then what we want to return, for now, we can just, we can print out nodes and just see if that gave us what we think it gave us. Okay, so now we have, that is like these instructions or these nodes broken up. But what I want to do is convert this into a 2-element array that's being returned from here, where the first element is the key and the second element is the value that we can then convert to a hash with 2h. So now we have AAA points at left and right, BBB points at left and right, and so on and so forth. So now what we want to do is we're going to start at some current node, and that's going to be AAA. And our goal, our like target, is ZZZ. And so what we want to do is find a path through these nodes, given these turns. We need to iterate until we reach ZZZ. So we might say something like until cur is equal to ZZZ, or the target, we want to set the cur equal to something, right? The cur is going to be nodes at cur, and then that's going to give us back the array. And then we need to figure out if we're going to go to the left or we're going to go to the right. This is going to give us left and right for the current node. And then we want to say maybe, so this list of turn characters is going to be LLR. And we want to start with L. And then the next one we want to do is L and then R. And then we want to go back to the beginning. There's a couple ways we could do this. One of them is we could say turns dot rotate. I don't know if I think one might be the default. I don't know. Let's see. If we open up IRB, let me just show you what this does. If we have an array of 1, 2, 3, 4, 5, and we'll call that A, and we do A.rotate, bang, then A, because we're using the bang, it's like rotating it in place and like actually modifying the underlying array. But you'll notice that like everything has been like shifted over. So now the one that used to be at the beginning is at the end. And if we run it again, oops, then it shifts again. So now 1 is second to last. If we rotate it again, 1 is third to last. If we rotate it again, 1 is second to last, and then it's back at the beginning. So by calling rotate every single time, it will shift around our turns. Okay, but before we do that, we want to see if turns.first is equal to L. And if it is, then the current becomes the left. Otherwise, the current becomes the right. And that's how we're going to iterate, right? And then at the end, what we want to know is our answer in this case for part 1 is how many steps it takes to get to ZZZ. So we need some counter. So we'll start our counter at 0, and then we'll do counter plus equals 1, and we'll print out the countdown here. And that should be our answer. So for the example input, it was 6. Let's grab our actual input here. Oops. Puzzle input. Grab everything, paste it in. And you'll notice that our instructions here are massive. We have lots of left, 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 blah, blah, blah. So now we can make our data be equal to data.readlines.mapchomp. And we can run this again. And we get back 15,989. 15,989 was part 1. So that's it for part 1. Okay, awesome. How can we make some improvements to this? Let's take a look. Right here, when we're doing this destructuring, we don't actually need to destructure, because if we go to the right, we don't use the left. And if we go to the left, we don't use the right. So what we can do is we can pop this in here and say, if the turns first says go to the left, then just discard the other one. And if it says go to the right, then discard that one. And actually, we need to make these occur. So this is like a way to say destructure the array value that's in nodes at current and pop in the left and then ignore the right if we're supposed to be turning left. Otherwise, ignore the left and pop the current in the right, and we should be good to go. So let's run that again. We get 1,580. That's like the right answer again, right? So we're doing well. So that's cool. This is like pretty concise, and we're able to rotate around our turns and move through a solution. Let's go to part 2. So in part 2, the sandstorm is upon you and you aren't any closer to escaping. It's going to take significantly more steps. Oh no. Anytime we see significantly more, we know it's going to be a lot of computation or something, right? What if the map wasn't for people, but it was for the ghosts, like the elf that disappeared? So now the problem gets harder, because we're going to start at every node that ends with an A. Instead of just starting at AAA, we're starting at every node that ends with an A. And we're going to follow all of the paths at the same time until they simultaneously all end up at nodes that end with Z. Okay. So when I first looked at this, my thought was like, okay, what we can do is we keep a list of all of the currents. So we have 11A, 22. And for each of the, I'm going to take you on a short path, a short journey to a dead end. Okay. We'll go back and implement the correct solution, but let me take you through my thought process when I saw this problem and I thought that I could solve it in one way that does not work. Okay. We're going to go down a path that does not work because it's inefficient. And then we're going to go solve it the right way that actually works. Okay. So my thought was, let's store, instead of having just current be one thing, let's store the list of all of the starting points. So we're going to say, instead of this being AAA, this is going to be nodes.keys.select, where the key, where it ends with an A. So this is going to be like k.end with A. Okay, so let's comment this out for a second, go back to our example input. But there's actually another example for this part 2. So we'll just pop that in here. Okay, so we're going to run it, and I guess we're not printing anything out. So p cur. Cur is just like shorthand for current. All right, so we got 11A and 22A. From our example up here, 11A and 22A are the only nodes that end with the letter A. So that is what we're starting with. Now, our same loop, it's going to look something like this. We want to iterate until, instead of current just being one individual value, now current is going to be this array. And so we need to keep track of which current we're on. We need to iterate through all of these current values, but we want to do so that we can update the array. The idea is that we'll go through one step at a time, and for each starting point, we'll check to see or we'll look at our turns and then go either to the left or to the right based on that. And then we'll update the current to be what our current position is. And we'll keep doing that until all of the values in current are equal to Z. When I first read it too, I thought, oh, this is going to be pretty simple because you can just go until one of them is equal to Z. But the reality is you need to keep going until all of the values are equal to Z. So if you look at the example here, if we go to the left first, so from 11A and we go to the left, we end up at 11B. We also need to go from 22A to 22B. That's one step, right? So at the end of step 1, both of our current positions would be updated to be 11A and 11B. And then in the next step, we're going to go to the right because that's the next turn. And our 11B needs to go to the right. So that ends up being 11Z. And our 22B ends up going to the right and ends up as 22C. But only one of the two pointers are pointing at a value that ends with a Z. So that is not a terminal case. And we can't just keep looking for the left because both the first and the second current need to be ending with a Z for us to call it quits. Oops. All right, so we want to iterate until cur.all c.end with a Z, right? Again, this is the wrong path. We're going down the wrong path. Okay, so let's again split out our left and right. We're going to say if turns.first is equal to the left, then we want to update, we need to iterate through cur. So cur.length.times do I. I wanted to iterate with a number reference into an index of cur because we're going to be modifying cur rather than iterating through the elements of cur. Okay, so now what we want to do is say, actually we can do this inside of this loop. So we're going to go through each of the different things for one step. And at the end, we're going to increment C because this is our step counter. So we'll just call C step. We no longer have a target. We know we're starting with the right cur. So until cur.all end with Z, we're going to iterate over each item. And nodes at cur. So cur is now, we can't use cur because this is an array. So we need to say the element is cur at I. So now we're going to go to nodes at I, and that will give us back a left and right. Now, if turns.first is left, then we want to update cur at I to be the left. Otherwise, we want to update cur at I to be the right. Now, instead of using turns.rotate here, we don't want to rotate every time. We only want to rotate for each step, right? we don't want to rotate for each starting point. We only want to rotate for each step because all the starting points need to move at once. I think this might actually work for, I don't know, let's see. Okay, end with undefined method end with for nil class. Cur p cur. Let's see. Oh, nodes at L. Okay. And this should be step. Okay, 6. So we got back 6. And what was the answer? Okay, so the answer for this example input was 6. So here we are. We're thinking, oh, great. We're moving right along. Everything is gravy. And then we go to comment in our test set, and it just hangs. And at first I was like, oh, gosh, maybe this isn't very efficient. So let's stop and think about this for a second. First of all, let's look at what cur is for our test set. Okay, cur is 1, 2, 3, 4, 5, 6. So we have 6 elements, 6 starting points, and all 6 of those starting points are going to have to navigate through and sync up to land at a Z at the same exact time, right? So then I thought, okay, what if we look at cur again? Let's just do the same exact thing that we had before, but just for one of these elements, right? So now we're going to have cur is equal to cur.first, while cur dot, it doesn't end with a Z. We're going to go through and count up how many we end up with for one single value, right? So we p step here at the end. This just ends up becoming cur. So you'll notice that this is the same solution we had for part 1, right? So just one value ends up being 18,157. So it's, that is a really big number. So it took 18,000 steps just to land on one single Z. Now, if we had this, and now if we just, let's say that we grab the second cur. All right, 14,000. So we have, I don't know, we're in the tens of thousands, right? And we need to land on the same Z twice. So what we need is the lowest common multiple, because we have to like go around. We have to keep going around the loop of turns until we perfectly align with all of the Z's. It's almost trying to align stars in the solar system, right? Or like the planets in the solar system or something. Like they're all going to go around at different speeds. So each of these different starting points are all different paths through the network that are all going to travel at different speeds until they hit a Z. And they all have to be lined up perfectly, all hitting a Z at the same time, or an ending node that ends with a Z at the same time for it to work out. If you think about it, they're all going to start at the same exact step. So that's like t equals 0 or time equals 0. And every time we take one step forward, they're all going to move in their own direction at a different time. And so if we think about, it's almost like one of those like rabbit and hare type situations where you're like trying to iterate around a linked list. But what we need to do is figure out when are they all going to be synced back up to 0? And that is, they all need to have a common multiple for the number of times they iterate around so that they all line up perfectly. So the approach that I took was to make a method here called find, and this is going to take in some cur and some nodes, and the turns, and we'll just return the steps for one single instance of this, right? So this is going to take in the current value. While the current doesn't end with Z, we're going to iterate through. And again, now we can flip back to our other clever one here. Okay. This is, I don't know. This is cool. All right. And then we're going to increment our steps, and turns.rotate. This becomes interesting, right? Because we don't necessarily want to modify the underlying array that is going to be used by some other future starting point. We need to be able to maintain turns without modifying it. So one way we could do that is like t equals turns.dupe or something. But an even better way is rather than using turns.first, we can use something else. So let's actually just start with p find cur.first with nodes and turns. And let's see. Okay, so step plus equals 1. Step doesn't exist. We've got to move step into here. And let's move this down here. All right, so that we're getting back an answer. I don't know. Oh, we're printing it out twice. We're printing it out here and here. Okay, 1001, oh yeah, 18157. That seems to work okay. But instead of rotating, again, what we want to do is we need to figure out where in the turns list we should be without actually modifying turns. And one way we can do that is by indexing into turns at the step, right? That'll get us, oh, if we're on the 0 step, we're at the first element of turns. But once we get to the end and we keep incrementing past the end of the list, now we need a way to loop back around. And so the modulo operator lets us do that. So now we can do turns.length. This is going to let us like loop around back to the beginning without modifying the underlying array. So this is just like another way to index into it. So we get the same answer back, which means this is still working the same. That's great. Now what we want to do is we want to go through each cur. So we can go through all of these .map, and we want to find k. And that should give us back some number, p cur. Okay, so it's giving us this list of numbers much faster. It actually completed. And these are all the number of steps that it takes from all of the nodes that end with an A until they hit a single Z the first time, right? As soon as they hit a Z the first time, this is the numbers that come back. Now what we want to do is find the lowest common multiple. And there are a bunch of different ways to do this. There's fancy prime factorization, math things that we could do to go try to figure out what the lowest common multiple is. But Ruby is amazing. And so Ruby has a method for lowest common multiple. So on an integer, you can call LCM and pass in another number as the argument, and it tells you what the lowest common multiple is between the first and the second. Isn't that so dope? And what's cool about this is we can chain them. If we want the lowest common multiple of 4 and 6 and 15, we can do it like that. And that figures out what the lowest common multiple is. It's pretty sweet. I believe the way that this works is it finds the greatest common factor and then takes the product of all these and then divides by the greatest common factor. And that's how you get the lowest common multiple or something. But rather than having to do any of the math ourselves, we can just map our list of numbers that came back and just use the LCM method, and that should give us the answer. So we run this. Oh gosh. And we don't want to map it. We want to inject it, right? Because we want to reduce down to some number. And holy moly, we get this huge number, 138309, blah, blah, blah. And I was like, that's way too big. That can't be right. But it's totally right. So that's how far we would have had to iterate and constantly updated cur until we got there, right? Now we're taking significantly more steps, as it said. But so we're like figuring out when the stars are going to align and then dropping that in. So I thought this was pretty cute. I don't know. Very concise. And I love that Ruby just exposes this method. Very cool. And then that also keeps our solution for part 1 and part 2 the same, because now we can just pass in to find. We can just say like our part 1 is like find AAA. Oh no, I guess not. I guess we need a different target, right? Ooh, let's modify this a little bit. Let's modify our find method to work for both cases. So one thing we can do is we can have our find method accept a block, and the block can be the condition that it's going to check for iteration. So here we can say while bang block.call with current, sure. And then when we pass in find here, it should be this block where it's like if C ends with Z, that's like our terminating condition. If we run this again, okay, we're missing some curly brace or something. Okay, so we get the same answer. That's pretty sweet. And then for our first section, we can say p find cur, or no, AAA, and then nodes and turns. And then for our block, we want it to be like C is equal to ZZZ. So now we should get our first answer and our second answer, and they both use basically the same function, but now we are using a block. We're passing a block argument here. There's probably another way that we could also count up the steps and return those cleanly, but I think this is good for now. So yeah, thanks again so much for watching. Really appreciate your time and attention. This was a fun one, and yeah, we'll see you in the next one. Cheers.